Okay. Excuse me. 1 point. Okay. Should be fine. Let's see. Sure. Okay, let's get started. Yeah, today we're going to talk about more details of global search algorithm and give the bit of and go over I guess a generalized version of Glover's algorithm that is content counting. Okay, and yeah, let's go back to what is Glover's algorithm. So Glover's algorithm is this algorithm that they use to solve the search problem. It says that if you have bigger than items, basically bigger than items, that's either 0 or 1, and the problem is to find any x. And so we think x are the index to those numbers. So x is something from 0 to bigger minus 1, and we want to find a big x such that f of x equal to 1. Okay. And or if there is no such x, then say it doesn't exist. Okay. And and then we have this global search algorithm that use order square root over m, where m is the number of x, such that f of x equal to 1. And for simplicity, we just say such x that we are called marked items. Okay, so we want to find any marked item. And the algorithm is pretty simple. So you start by creating the equal superposition of all states. So we start with 0 to the small n, and where we assume 2 to the small n equal to big N. If big N is not a power of 2, it's not too different. We just need to change a little bit. Okay. And anyway, so assume big N equal to 2 to the small n, and we create equal superposition of all computational bases by doing a whole bunch of header mask. And then we just repeat this either called Grover diffusion operator or Grover iteration. Okay, we could repeat this so-called Grover iteration that composed of 2 reflections. First one is this OF, is just you apply the oracle, and the second one, so you return in 3 complicated steps, and about the second step together is just this reflection around this side as a uniform superposition of everything. Okay, so first you apply oracle, and the second step is this 2 projector 2 side minus identity, which is a reflection around side. Okay, and yeah, as you said, this Grover iteration is just you apply oracle, then you apply 2 side minus identity. And we see that in the geometric view. Okay, so and both the oracle and the psi is a reflection. Oracle is a reflection around this alpha. That's that's a superposition of unmarked items, and where beta is a superposition of marked items. Okay. And then we see that 2 reflection equal to 1 rotation, because you reflect around psi, you go down here, and then reflect around alpha. You reflect around alpha, you down here, and then you reflect around psi up here. And because alpha and psi has this angle theta over 2, and so what you do is you rotate your state by angle theta. Okay. And yeah, so those 2 reflections will keep angle theta to your state, and you start with this uniform superposition psi. And so we know at some point you will get very close to this beta state, which is superposition of every marked item. Okay, and then we see that how many rotation we need to do how many global iteration we need to do to get to this beta, to get close to beta, is this R is order square root n over m. Okay, and the next time we end with two questions. First is what if we don't know m, and what's the error. Okay, and yeah, and we are going to go over that today. So any questions so far? If not, yes. And let's start with the probability of success. Okay. And as we say, so after we do k global iteration, our state is this cosine 2k plus 1 over 2 theta alpha plus sine 2k plus 1 over 2 theta beta. So basically our angle is this 2k plus 1 over 2 theta. Okay. And so now we think about this state and what happened we measure. And so this we don't actually do, but for for simplicity, let's think about what if we measure in alpha beta basis. We can actually do this. And so in this two-dimensional basis, we see that if we are able to measure in alpha beta basis, then you will get the beta with probability. I guess you can kind of do this, but anyway, if you measure in alpha beta basis, then you have some state here with the angle 2k plus 1 theta, 2k plus 1 over 2 theta. You have some angle here, then the probability getting alpha is just cosine squared this angle, and the probability getting beta is just sine squared this angle. Okay? And you can also see here the amplitude of beta is sine, and the amplitude of alpha is cosine. And so the probability you get beta is just sine squared this angle. Okay, and so similarly, because beta yeah, I guess alpha and beta are separated in computational basis, and so you can very easily see that. I guess the better way to say this is because alpha and beta are composed of different computational basis elements, and so you think about just measure this state in computational basis, then you will get a random x, and this x will either be some this x will either be a marked x that's an x in beta, or a marked x that's an x in alpha. Okay. And the probability of you got x that's inside beta, a marked x, is just the same probability. The same probability sine squared 2k plus 1 over theta. Okay, and yeah, so that's the success probability, and obviously the further probability is you measure in computational basis, and you get something that is component of alpha, and the probability just is cosine squared this angle, so cosine squared k plus 1 over 2 theta. And then we can do some trigonometry to relate it to our number we know. So first, the cosine square is, well, cosine theta is sine pi over 2 minus theta, and yeah, and then we change this to the value delta. Oh, sorry. Yeah, sorry. So I guess we call this phi. So sorry, one more typo. Yeah, and so this number we call it. This is actually minus phi. Okay, and so this is overshoot angle. So this angle minus pi over 2 is the overshoot angle here, and then we said before. This overshoot angle should be less than theta over 2, otherwise you can just stop early. And yeah, so this should be less than sine squared theta over 2, and sine squared theta over 2 is just n over n from this relationship here. Okay. And yeah, so we see that the further probability is, so in the end we get the further probability is less than equal to n over n. And so we see that if we don't have too many mark items, and we won't fail. Okay. So I guess as n goes to infinity, the failure probability goes to 0. So the failure probability is pretty small. Okay. And yeah, also it's easy to see that if n over n is say a constant, if this thing don't go to 0, then this means that there are a lot of mark items, and you can basically just solve this by classical algorithm, just keep sampling. Okay, just keep doing random sample And yeah, so that's the probability of success. You see that it's pretty high. And and then now there is a bigger problem is that we don't know m. Okay, and so the algorithm can overshoot. And so here is a plot of the success probability we have here. So success probability is this sine square sine square angle, and so if you just plus sine square, okay, sine square angle, and the angle is linear in k, and so if you plot this probability of success with k, and then you see then you have this sine square function which go from 0 to 1. Okay, so it goes up and down, and you see you get a maximum success probability around pi over 4 square root over m. Okay, and now the problem is that you want your k to stop here, but you don't know m, then you don't know where k to stop. And so if you keep going this, then you will, so if you choose a k that's larger than this value, then you see your success probability actually goes down. So your probability will go up, down, okay? Okay, and that's annoying, but let's deal with other things first. And that's the error probability. So we see that we have a pretty small error probability here. Because it's small, it goes to 0, as it can go to infinity. And but if you want to have a zero error algorithm, so you want success probability to be 100%, then actually you can make the theta a little smaller. So you kind of stretch out this success probability a little bit, graph a little bit, and yeah, and you can make the the optimal rotation. These are equal to pi over 2 divided by theta minus 1 over 2, okay, to be 0. So basically, I guess it goes to this picture. So we say we overshoot a little bit, but a little bit here, and making us having error. But if you make your theta just a little, being a little smaller, and everything a little bit closer to alpha with the exact number, then you can have your angle here. You can have this less edge here to be exactly on pi over 2, and then you have no error. Okay, so that's a good thing you can do if you know m. Okay, and if you don't know m, and then there are several things you can do. And first is I guess you can do quantum counting. And so this is the thing we're going to do. So basically we estimate n first, and then use the estimated n to do this Grover search, and to rotate to some place that you think is about correct, and just measure it. Okay, so quantum counting to do SAN first. And the second one is it's easier. You can do kind of binary search. Basically, you use natural search with your guess of n. Okay, so you start with guessing m is something very big, and then you exponentially decrease the guess of m you have. Okay, so start with n equal to n, and you guess it, and try to search for your angle. Then you start guessing n equal to n over 2, n over 4, etc. Okay, and and the time competency factors. And so if you keep doing this, you think you are going to do a lot of different m, but actually so you are going to so the sequence, so from n and h1 divided by 2, so the sequence you get here, there are log n of them, and but actually you don't get the extra log n factor. Okay, so you need to do Grover search a lot of time, but actually you only get this 1 over about 1 over 1 minus square root 1 over square root factor. Sorry, I think I have too many square roots. It should be sorry, typo. It should be 1 over 1 minus square. 1 over just 1 square root here. Okay, 1 over 1 minus 1 over square root. Okay, and you get this extra factor because you get the number of iterations you try is a geometric series, so just a constant factor. Okay, and because so basically the number of iterations you try is 1 about 1 if you have n equal to n, and then it's about then when you increase when you decrease n by a factor of square root 2, you can decrease your n by a factor of square root 2, and if you decrease your n by a factor of 2, because the number of iteration you try is square root n over n, okay, and so this I write this wrong. The number of iteration you use is order square root n over n, okay. So if your n is divided by 2, then the number of iteration you do is grow by square root 2, and yeah, and so you keep doing this, you have a larger and larger n, and then the number of iteration you do will be growing with a factor of square root 2 each time, and until you go to a number that's around about order square root n over n, and here you should find your mark item, okay? Because we say if you use this number of iteration, you have very high probability to find the mark item, okay? And so you sum up this series, then you see that this is a geometric series ending with square root n over n, and so that's about order square. That's about square root n over n times this extra constant factor. Okay, and yeah, so that's the a way to do global search without knowing n. Okay, and so we can do this binary search, but content counting by itself is fun, and useful, and so we are going to talk about content counting for the rest of the class today. Okay, so any questions so far? If not, then let's go to content counting. Okay, so content counting, as we said before, what this do is we want to SAM. Okay, so our setup is very similar to global search. So we have some f as our code, that's a binary Boolean function from 0, 1 to n to 0, 1, and we want to SAM such that n, that's the number of x. Number n, that's the number of x such that f of x equal to 1. So I guess I should put this number here. Mark a little. So m is the number of x such that f of x equal to 1. Number of x. Okay, and here, and here we say estimate because as we are going to see, we are not able to exactly get n because that will require a lot of query. Basically, you need to look through everything. Okay, and so what we do is we are going to get an estimate of n up to some error that we're going to say, and the error model we take is that we will have epsilon multiplicative error. Okay, and this means that if we have some estimate, if our algorithm will output estimate of n, let's call it m tilde, and we mean that m tilde minus m should be epsilon should be less than or equal to. So this is the error you got on your estimation, and so we say the estimation should be error less than epsilon. So multiply your HO value. So that's what we mean by multiplicative error. Okay. And yeah, so this is meaning of epsilon multiplicative error. Error is epsilon multiplying on your HO value. Okay. Epsilon multiplicative error. Okay. And yeah. So I guess I should write theta here. And it's shown that quantum algorithm can do this pretty fast. Can do this in theta. 1 epsilon square root n over n queries. Okay, and so I think let's try to say this thing makes sense. So first of all, this is about the same query complexity of doing Gover search. So you have a square root n over n, and also you have an epsilon factor here. That's just excuse me. You have this 1 over epsilon factor here, and this kind of makes sense because you know that if you want higher precision, then then you should use more queries. Okay, and and I believe this is both query and this is query complexity and also time complexity, and also this is quadratic speed up, just like a classic, Gover's algorithm. This is a quadratic speed up over the classical algorithm. So you can show that classically by some statistical argument. Classically, the query complexity is theta, just everything squared, epsilon squared over n over n. Okay. So quantum counting also got a quadratic speed up over classical counting. Okay. And so that's about quantum counting, and then how this how this algorithm work is actually pretty simple. So it has two components, and so it actually use the algorithm we talk about last chapter. That's the phase estimation. So algorithm is apply phase estimation, and so this is related to Gover's algorithm, and so you do phase estimation on your Gover iteration G. And just as a reminder, Gover iteration is this thing. So it's two reflection. So first reflection around OF, reflection is OF, that's the oracle, and the second reflection around your uniform superposition state side. Okay, and so that's the quantum counting problem and how algorithm is going to do. Okay. Any question from the setup of the problem here? I think we are going very fast. We are able to finish the class very early today. And but anyway, so that's the quantum counting. We good? Quantum counting problem. We want to estimate the number of mark item m. Okay. And then let's go to our analysis of this quantum counting algorithm. Okay, and so what is Gover iteration? As we say, Gover iteration is two reflections, and as we shown before, the two reflection equal to a rotation. Okay, so Gover iteration is a rotation theta in the space that we care about. That's in a space of alpha and beta. Okay. And I guess I forgot. And so Gover iteration is a rotation of angle theta. In the 2D subspace we care about this plane spanned by alpha and beta. And so rotation you can return it as a matrix is this. Okay. So rotation matrix is just cosine theta minus sin theta, cosine theta. And then you can do your linear algebra to calculate its eigenvalue. And you see that the eigenvalues are ei theta and ei 2 pi, sorry, e to the I theta and e to the I 2 pi minus theta. Okay. And also we have some reminder here. So remember sin squared theta over 2 equal to n over n. So theta will be about 2 times the square root of n over n. Okay. And so I guess here we should say something extra. Okay. Here we should say, and so we say we want to do phase estimation. Okay. So if we phase estimation and we want to phase estimation on something that is two-dimensional subspace, because everything is very nice in this two-dimensional subspace, and so we do phase estimation on something we know inside here. That's this uniform superposition state side. Okay, and because as we said before, I guess if we go to about here, and as we say here, this side state is a linear combination of alpha and beta, and so it's in this plane. Okay, and so if we pick psi as the if we pick this psi as the quote eigenstate of phase estimation, and then psi will be the superposition of eigenvectors for either this eigenvalue or this eigenvalue. Okay, and and then we do just some notation thing. Okay, and so this is a bit funny. So we want to, here we use funny notation, so we will actually use 2n to replace n. Basically we increase the size of n, and I guess here we are without changing m. Okay, we want to fix m and make n twice as large, and it's pretty easy. You just add a whole bunch of items that's not mark item. So you have your mark item, and then you think about your truth table of f. You can append a whole bunch of 0 at the end, so that the n is twice as large with a lot of 0. Okay, and we want this. So basically, we want this n over n to be at most 1 over 2, and in that case, then you can show that theta will be less than pi over 2. Then the calculation is a little bit easier. I think this is unnecessary, but we just say we can do this to make the analysis a little easier. Okay, and then yeah, so phase estimation. Then we have the state that we want to phase estimate on. This is like the eigenstate, and then we need to pick our t, and so we pick t equal to m plus this log 1 over delta vector. Okay. So as we say, so psi as psi equal to, as we said before, psi equal to superposition as the input for our phase estimation. And so n will be number that we'll be choosing later. So and when n is larger, then you have more accuracy to your quantum counting. Okay, and basically at the end we'll analyze the cases for different m and see how the number query and and the accuracy of our quantum counting got trade off. Okay, and and as we said, because psi is in this two-dimensional space, and the only eigenvalue in this two-dimensional space is either theta or 2 pi minus theta. Okay, and so you will learn either theta or 2 pi minus theta to accuracy 2 to the minus m, because that's what the phase estimation guarantee. M is the precision. Okay, and that means delta theta will be less than 2 to the minus m. Okay, and with the probability of success 1 minus delta. Okay, and then we can assume that we just get theta because we know theta is less than pi over 2, and that means this 2 pi minus theta is greater than 3 pi over 2. Okay, this thing is greater or equal to 3 pi over 2, and I guess less than or equal to 2 pi, and this thing is between pi over 2 and 0. Okay, so that's right. So this thing is between 0 and pi over 2. Okay, so we can clearly see which one we are getting, and if you see something like this, you just have 2 pi minus this thing. Okay, and so we can assume that we just get this eigenvalue, theta. Okay, and then we are left with calculating what's the relationship between m and your accuracy in this small, your peak of small m, and your accuracy delta m. Okay, and the delta m is the difference between m and m delta. Okay, I said this is the error of your counting, okay, of your estimate of m. Okay, so m is the error, and so similarly we define this delta theta, although we already call it, but now we say it more formally. So delta theta is the difference between actual theta and the estimate of theta you get from phase estimation. Okay, And as we said before, just by the guarantee of phase estimation, delta theta is going to be less than 2 to the minus m. Okay. And then now we are just left with complicated calculation here. Okay. And so we start with, so basically we are going to relate this delta m to the small m here. Okay. And so let's write our strategy here. So we are going to relate delta m, wrong writing. So we are going to relate delta m to delta theta, and then we know delta theta is bounded by small n, so that will relate to the m, small m. Okay. And here, if you just do it high level, it's pretty easy, but we do this in detail. Okay. Detail is a bit annoying with a whole bunch of trigonometry. Okay. And yeah, so we start with the sine squared theta over 2 equal to n big N over 2n. Okay, so it was big N over n, but we stretch n by a factor of 2, so it's 2n now. Okay. Okay, so sine squared theta over 2 equal to big N over 2n, and then we think about what is this delta m over 2n. So we kind of do kind of calculus thing. So we think about what's the delta m. So delta m over 2n. So if you have delta m, yeah, so you have m tilde minus m here, and then you should have the same difference here. Okay, so you should have sine squared theta tilde minus sine squared theta. Okay, this is just by I guess really nothing. Okay, so this is yeah, you have a difference on right hand side, and you also have a difference on left hand side here. Okay. And yeah, because the only thing can get difference is theta here, and so you can have theta difference, having difference here, and m having difference here. Okay. Okay. So here delta m being m tilde minus m, and on the left hand side you also have the term with theta tilde minus the term with theta, and here we just write down. So I guess here we are implicitly saying that we have theta tilde equal to theta plus delta theta. Okay, and yeah, so it's sine squared theta plus delta theta over 2 minus sine squared theta over 2. And then here we just have a squared minus b squared equal to a plus b times a minus b. Okay, and yeah, and I guess here I should, oh, doesn't really matter, and but to be a little more precise, I should have less or equal to, because we are adding more absolute value. Okay, less equal to, and then now we bound those two terms separately, and by a whole bunch of trigonometry identity, and so we actually bound the difference term first. So we have sine theta plus delta theta over 2 minus sine theta over 2. And then here we just use the sum to product formula. So sine A minus sine B equal to 2 cosine A plus B over 2 times sine A minus B over 2. Okay, so A is the theta plus delta theta over 2, and B is the theta over 2. And you plug in a formula, then it's cosine theta over 2 plus delta theta over 4. Times this sine, and the difference is delta theta over 4. Okay, and then we just take a whole bunch of things with the absolute value. Then you know cosine any angle will be less than 1. Its absolute value is less than 1, so just throw it away with this less than or equal, and then we are left with this 2, and then sine delta theta over 4 we say is less equal to delta theta over 4, because with absolute value, because this basically is sine x is going to be always less equal to x. Okay, and yeah, so you have a 2, and this sine delta theta over 4 become absolute value of delta theta over 4, and yeah, so this is easily seen as delta theta, absolute value of delta theta over 2. Okay. and then so that's the second term, and the first term you have a excuse me, you have a sign plus sign, and I guess we are I'm missing one term, sin theta over 2. Oh, never mind. So I guess the first term we are doing this a bit funny. Okay, so first term, so we get the first part of first term. Okay, so I guess we break the first term equal into the sin theta over 2 plus the absolute value of sin theta over 2 plus the absolute value of sin theta plus delta theta over 2. Okay, and so the sin theta plus delta theta over 2 is we use sin A plus B, then is sin A cosine B plus cosine A sin B. Cosine A sin B. Okay, and so this is less equal to, and then we just drop all the cosine terms, because once again cosine is less equal to 1. Okay, so this is less equal to sin theta over 2 plus plus this sin delta plus sin delta theta over 2, which is less equal to delta theta over 2. And I think it's here we use the fact that theta is between 0 and pi over 2, so that we can drop the absolute value sign here, because we know sin theta over 2 is going to be greater or equal to 0. Okay, and so we have this. Then we combine both of these things back. So the first term become this thing plus this thing. Okay, and so we have twice sin theta over 2 plus delta theta over 2. Okay, so so twice of sin theta over 2 and plus delta theta over 2, and the second term we bounded just delta theta over 2. Yeah, delta theta over 2, and and then finally we can make everything to what we want. Oh, and so we are missing a whole bunch of absolute value here. So here every delta theta should be inside absolute value, delta theta and delta theta. Okay, and yeah, and so then we just change every term to m and n. Okay, and we know that sin squared theta over 2 equal to n over 2n. So this sin theta over 2 is just the square root of n over n, and you have square root 1 over 2 inside square root, and 2 here. So this is square root 2n over n. And then for those delta theta, we can now bound to small n. Okay, and we know delta theta is less than 2 to the minus n, and so the delta theta over 2 is just less than 2 to the minus n plus 1. Okay, and then so we have this delta n absolute value is over 2n is less than this competitive formula. Then we multiply 2n by both sides. Finally, we get our bound on delta m. So delta m is less or equal to when you multiply the 2 here, so you get rid of this plus 1 here, and multiply n, then this becomes square root 2nn, and the second term becomes n times 2 to the minus n plus 1, and everything is multiplied with 2 to the minus n. Okay, and yeah, so I guess this is I should put it larger, but this is the formula we finally get. This is the important formula we get. Okay, any question? And yeah, I guess we will start very early today. Okay, and with this thing we can now bound the number of query with everything. Then now we can bound. We can see how. Now we have this formula between n and the small n and delta n, and then we can start thinking about what's the number of query we use in this algorithm. Okay, and so remember the algorithm in this is basically phase estimation, and you have the phase estimation with the first register having t qubit, and you do this control, you do a k here, and with psi on second register. Yeah. And now you see that the phase estimation, the number of query you need to do. So this you need to do here is actually about 2 to the t, because this k can go from 0 to basically 2 to the t. Okay. So number of queries is 2 to the t, and this is very different from what we do in Grover's algorithm, because we say Grover's algorithm can do this in basic order t very efficiently. That's because we are able to do repeating squaring. Okay, but here because the u is given in oracle, and so there is no such thing as repeated squaring for just whatever arbitrary oracle. So so this global iteration, you actually need to do this if you want to do it to some t's power, to some very large power, to some k's power. You just need to do it k times. Okay, and yeah, so number of query here will be about 2 to the t, and 2 to the t. If you go back to what t is n plus is order log n plus order log 1 over delta, and so we put 2 to the t, put everything up to the exponent of 2. Then you see 2 to the t is about 2 to the t is about 2 to n times order 1 over delta. Okay, and so if you fix delta to some constant probability, then you see that 2 to the t is about order 2 to the n. Okay, so number query is about 2 to the n. Okay, and now we start to, so we have those two things, and so now we have those two things, and we can start tuning number of query to see what kind of error we get. Okay, so these two things, and so the first is let's go to the precision we want as the start of class. So if we have delta m equal to epsilon m, where epsilon is some constant multiplicative factor, and then you try to solve this here. So you see it's very complicated, but actually it's pretty easy to see that this second term here is going to be pretty small all the time. Okay, so if we ignore the second term here, then you just have epsilon m is about 2 to the minus m times this. So I guess I use the tilde notation to be like an order, so we ignore the constant factor. So it's about 2 to the minus n times square root of n. Okay, and then you have so you move things around. You have 2 to n equal to this number we said at the beginning of this section. So 2 to n is 1 over epsilon square root n over n. Okay, and we also say the number of query is about order 2 to the n, 2 to the small n, and so number of query is about order 1 over epsilon square root n over n. Okay, and we just check do a bit of checking here. So we claim that the second term here will be small, and let's see that's actually the case. So we already calculated what's the 2 to m here. Okay, and so we say we pick 2 to the small n to be this number, and let's plug in this here, and then we see that the second term give you that so the extra error you got here, the extra error you got from adding this term back is n times 2 to the minus n plus 1 times 2 to the minus n. Okay, and that's about n times 2 to the minus n 2n. So if we are getting rid of if we are skipping all the constant factor, so n times 2 to the minus n, 2 to the minus n, or 2 to the minus 2n, and so that's n times this inverted squared, so that's epsilon squared n over n. Okay, so n cancel, so that's order epsilon square m, and that's much smaller than this this epsilon m here. So yeah, so this is about epsilon square m, and that's much small. That should be much smaller than epsilon m. Okay, for small epsilon. Okay, so you see that the second order term, it should be okay when we do this approximation here. Okay, and but this algorithm, and okay, so this quantum counting algorithm kind of does what we want to do. So we use this number of query to estimate m to epsilon error. But this is once again funny because to do this you need to pick the t to be exactly pick the t or pick the m you want exactly, right? You need to have enough precision t to get this m. Okay, but here you see that the small t and the small n actually depend on big N, and yeah, so this gives us the issue here. Because if you know big N, then you don't need to do counting anymore, right? Big N is something we are known here, so this is a problem with using this to get big N, because you cannot pick the the good enough t to do this. Okay, and so I guess here once again, to solve this issue, you can do some kind of binary search as we said in the Grover algorithm. Okay, kind of defeat the purpose, but you can know it. Okay. So kind of binary search, that means you pick your t from small to large, and to estimate your m. Okay, and yeah, that's a bit annoying. But let's see some more useful case. Okay, and then once again, as we say, classically, you need this one based on square and one query. So if you are going to be able to do this, then you get a square root speed up. Okay, and for other case, is that if you want delta m equal to 1, so you want to have basically exact counting of your output number. You want yeah, so basically you want exact counting, so not approximate counting anymore. You want to n to be accurate up to just 1, and then you see that the q you need is about so you want to see this thing to be 1, then your 2 to the minus n should be order 1 over square root n. Okay, and that means 2 to the m is about order square root n. Okay, and yeah, so this is pretty large usually. Okay, and yeah, so again, this thing also depends on n, and in particular, if your m is very large, if your m is order n, then you see that it's hard to get exact count of the number of market items you have. Okay. And yeah, so you got no quantum speed up is m is order n here, and you want exact counting. Okay, and then let's see, the case we have is that let's see, a case we want to do the Grover is you can pick a number of query to be something in terms of n. So if basically you just pick something. Basically you pick the worst n possible. Okay, and so if you pick q equal to square root n, so kind of so this is basically assume constant epsilon and n equal to 1. Okay, and in this case you will get your delta n is actually a little better than constant epsilon. Okay, yeah. So you pick q equal to square root n, and delta n will be about order delta will be order delta n. Sorry, delta n will be order square root n. Okay, and then you can show that. Let's see. So this is square root n. Yeah, yeah, and the delta n will be about order square root n, and then this is enough to do Grover search. You can show that this gives you just constant error on Grover search, and so if you use the square root and queries to estimate the n, then yeah, then you can do global search. And this is another way to show that global search can be done in order. This will be a proof that showing that global search can be done order square root n. But yeah, it's so this is what claimed by the textbook. But this is actually a little suboptimal than the binary search method we do here, because this method will give you order square root n over m. So when your m is larger than constant, then binary search here is still a little faster. Okay, and yeah, so this is some interesting quantum counting algorithm, and it left us a little unsatisfied. But I guess let's take a 10-minute break. We're almost finished, but let's take a 10-minute break and finish the next few slides. Quickly in next class. Okay. Yeah, let's take a break.需要做的乘法是有4的，但我不知道搞错很多，就不要到有3的，就不要变有2。但是不管怎样，它都会有3的。
哦，反正它就是包括是。
可是我之前没有想，因为还有搞错上去。不知道是有3还是有2，我觉得有可能是有2，可能要看一下课本。看一下课本。你要做很多。还是都出来。Product can be computed using L3，或者抄它的L3。可是我写的是什么？看一下。哦，所以应该是L2吗？它L2是什么来着？
所以他是说单个是
单一个是L2，然后加L3，对吧？
然后，
所以我应该是会L2才对。哦，因为乘法自己也要有就是这样。
所以这全部是只有3到7。
应该是这样。好的。这个东西要这个都是有的。 嗯，哦，不是这个，哪个记错了？可以吗？哦。Okay, I guess let's get started and finish this bit of today's lecture. Okay, and yeah, so we see we have this quantum counting algorithm that does phase estimation on global iteration, and with different t, you get different precision on UM. Okay, you have you pick a different number of bits in your phase estimation, and you can get different precision on UM. Okay, with basically this formula. Okay, and but if we want to get constant, okay, and yeah, with this kind of accuracy, and it's a little bit of unsatisfied unsatisfactory here because you see that you need to, if you want to have some constant multiplicative error but doesn't know m, then you cannot quite pick the optimal t here. Okay, and so there are ways to overcome this. Is actually a pretty recent paper. This quantum approximate counting simplified paper by Scarlett and Petrillo, and but they actually do this for different motivation. So this M motivation can be dealt with in other way, and but their motivation is they think that quantum counting is actually some procedure very related to Grover's algorithm, and it shouldn't relate to, actually don't relate to quantum Fourier transform that much. Okay, it feels like you should be able to do quantum counting with only Grover-like procedure. Okay, and indeed that's possible. Yeah, and this has some critical the product where we don't want to do quantum Fourier transform has some critical implication because quantum Fourier transform is just a pretty hard circuit to do. Okay, and yeah, in particular we cannot do quantum Fourier transform in near term in our near term circuits, near term quantum computers. Otherwise, we will already be able to do factoring. Okay. So if you don't want to do quantum Fourier transform, then and also if we don't know m, then we can still use the algorithm to do quantum counting. Okay, and yeah, so they have this algorithm that basically just run different Grover iterations with a suitable number of. So they have a bit of a complicated schedule saying that if you do the appropriate number of Grover iteration, so basically you rotate your, go to the Grover, yeah, so you just keep rotating your side to some good number. Okay, so you just keep rotating side to some number and see, and measure it to see it's marked item or not marked item. And so if you pick the number of rotation carefully, then usually you can do quantum counting, quantum approximate counting with the number with the complexity we can here. Okay, the complexity we can here, and without knowing m in advance. Okay, and so that's very nice. So if you want to learn how it works, you can read this paper. Okay. And it has a little bit of overhead in computational complexity, in the time complexity. Okay, and yeah, so that's quantum counting. We have something that almost work, but missing a little bit. I think we can also use a binary search here. Okay, but if we want a simpler algorithm, then you can actually just do Grover rotation with good angles, and yeah. Then you can estimate m to the accuracy you want. Okay, and that's about quantum counting. And then lastly, today we want to talk about some application of Grover's algorithm. Okay, and so the simplest application you can think about is for solving a P problem. Okay. And so recall that NP problem is a problem that you can verify efficiently. And by verify, it means that so your instance, so NP problems are decision problem. You have a yes instance and no instance. And we said that yes instance can be verified because for every yes instance, there is a witness that will convince you that can easily convince you that the instance of X is a yes. Okay. And yeah, so every yes instance X, there is a witness W such that you can check X is a yes instance by running this polynomial time algorithm M with the witness. So you can check N over WX and it will tell you yes if X is a yes instance. And on the other hand, for every no instance and for W you put in this checking algorithm, it will tell you that the checking algorithm will tell you that is will tell you yes. Okay. And anyway, so there is this polynomial size witness W that you can put in your checking algorithm to check use this witness to check your input is actually a yes input. Okay, and so let's say if your witness is length m, and brute force way to solve NP problem is that you given some witness x, you just search for every possible witness to see is there any witness that let your checking algorithm pass. Okay, and yeah, and let's say the length of W is m, and we can always build because this m is just a polynomial time classical algorithm. Then you can always build a polynomial time classical algorithm into a quantum algorithm. Okay, and then we just call the quantum algorithm an oracle. So you can have a quantum oracle for m, such that basically does what a quantum oracle do. Okay, so so you can compute this f of w. So this f of w actually depends on x. So you say this f of w equal to n of wx. Okay. So that we are just so this f of w so this f depends on x, but we are just not writing x here to make the notation simpler. Okay. So you can build the f of w that checks every w for your input x. Okay. And so what happens is that you can build this O sub f on O sub f, which on computational basis w will give you this factor -1 to the n -1 to the n wx of w. Okay, and with this OF, then you can do global search over all possible w. Okay. Then you can do global search over all possible w for some w such as n over wx equal to 1. So you are basically searching over a witness that will verify that x is a yes instance. Okay, and so if this this witness is found, then we know x is a yes instance. And by the promise of NP problem, if x is a no instance, you cannot find such witness. Okay. And so this global search will solve your NP problem. Okay, and then finally, how many witnesses you need to search is 2 to n over 2, because global search has a square root in its query complexity. Okay, so classically they are total 2 to n. Okay, because we assume w has a length m, so there are totally 2 to n possible w. So classically, you want to brute force solution here, you search over OW, and there are 2 to n of them. Okay, but quantally, because you global search over them, so you still need to use the exponential number of calls, but it's much smaller. So you only use 2 to n over 2. Okay, so we see there is some small quantum speed up in solving a P problem. I guess it's sometimes it's not quite small. You have a quadratic speed up. Quantum speed up over classical brute force algorithm. Okay, so that's some application of global algorithm. Just one of the application, one of the simpler application of global algorithm. That is, you can brute force search NP problems by just searching over all witnesses. Okay, and but there is some caveat here. That these don't prove that global algorithm give you a quantum speed up for every NP problem, because what global algorithm do is it give you this 2 to n over 2 problem. But for some NP problem, there are classical algorithms that are smarter than just going through all witness. They have a smarter way to go through witness, so sometimes there is no speed up if you use this way. Okay. And yeah, so I believe we will end very early today if we have no question. So that's all the slide I have today. And yeah, so this will be all I have today, and that's all I want to say about global algorithm for now. I guess the upper bound of the global algorithm. And next week we will go into the most technical part of this course, that's proving that global algorithms are optimal, and that means I'm going to give you quantum lower bound of the search problem. Okay, and yeah, so see you next week, and we will end early today.